A 300-gram mass on a 30-centimeter long string oscillates as a pendulum. It has a speed of 0.25 meters per second as it passes through the lowest point. What maximum angle does the pendulum reach? So we're talking about simple harmonic motion and the simple pendulum. So I'm going to assume that we're in the so-called small angle limit. That is to say, the small angle approximation is appropriate. If you recall, that small angle approximation tells you that sine of theta is approximately equal to theta, and that is true if theta is small enough. Just make sure that the units for theta should be in radians if that equation is going to make any sense. So assuming that's true, what we have is the concept of simple harmonic motion. Simple harmonic motion, SHM. And we also have to deal with a simple pendulum, in particular, results from the analysis of simple pendulum. And because we can see that there is angular motion, but also some mixing in of linear motion, we're going to need to think about the linear to angular motion connection. Okay. So, simple harmonic motion, simple pendulum. What we have here is a relationship that the angular frequency for a simple pendulum is given by the square root of G over L, where L is the length of the string. And again, for a simple pendulum, this assumes that the mass is all the way at the end. Now, this is simply related to the period of the pendulum in this way, in case we need it. And what I want to do now is something a little unconventional. I want to put this in quotes. I'm putting the angular frequency in quotes because we have actually two symbols with omega that I want to try to disentangle. For one thing, here we have simple harmonic motion, which will describe the motion of this mass as it goes back and forth and back and forth. And there will be a function that describes that motion, and that mathematical function has an angular frequency, which you should think of mathematically in terms of something that spins around, but only mathematically. Separately, we'll have the actual angular speed of this mass as it swings back and forth, which is changing all the time. Let's put this in equations so that we can make some sense out of it. Since we have simple harmonic motion, remember that the result of an analysis of that tells you something like the position of a system, the position of an object in this simple harmonically oscillating system, has an amplitude, and then it undergoes sinusoidal oscillations that can be described with, for example, a cosine function. And that cosine function can be written as 2 pi over the period of that motion that get multiplied by the time, and then there may be some phase shift that I'll call phi, something that offsets that. For us, when we're interested in knowing what is the angle theta as a function of time, we can write this in this way. Let's write it as, instead of A, we'll write this as the maximum angle, and then multiply that times the cosine function, 2 pi over the period of the pendulum, which is square root G over L, and that gets multiplied by time. There could also be a phase shift here, but let's assume that the object starts perhaps at its maximum angle and then swings back and forth, so we don't have to worry about the phase shift. In doing this, I've been able to neglect writing omega p, which I think could be confusing here. This cosine function tells us how the object will swing back and forth and how the angle will change in time. And that's what we should focus on using for now. So we have results for simple harmonic motion, and we have results for the simple pendulum, which simply relates the period of motion to g and the length. The last thing to do is remember that linear motion and angular motion are related, and they're related in this way, that the linear speed, which is going to be a function of time, is related to the angular speed, omega, and the proportionality constant is the radius of the circle that they go around. The radius of that circle here is the length of the string, and so I should write it in this way. And with these two equations, we should be able to solve for what we want. Here's what we have to keep in mind. that omega of t is defined as the derivative of theta with respect to time. And if I take the derivative of theta as a function of time, I discover that I get a theta max times a minus 1 times a sine. Inside the sine is the same argument, square root g over L times t, and then I multiply by the square root of g over L. So cleaning that up, we have a minus square root g over L theta max times sine of square root g over L times the time. Okay. We need to figure out some relationship between the maximum speed and the maximum angle. Let's try to think about what this equation tells us. This says that the maximum speed, and by speed I really do mean speed, let's forget about whether the velocity is negative or positive. This should be given by the absolute value of L, which doesn't change, and the maximum angular speed that is possible. The maximum angular speed that is possible we can figure out by looking at this equation that we just determined for the angular speed as a function of time. Notice that the sine can never be bigger or smaller than minus 1, so the maximum is equal to 1. And so what remains is this for the maximum amplitude. So when I go to determine what is the maximum speed, I'll put in L and the maximum omega, which is square root g over L times theta max. Square root g over L times theta max. Okay? Now, I could stick in the minus signs, but that's not really relevant at this point. Let's summarize what we have. What we just determined is the maximum speed should be simply related by L square root g over L times theta max, which we can simplify a little bit and write this as the square root of Lg times theta max. Now all we need to do is rearrange and solve for theta max. When we plug in the numbers that are given to us, notice the mass is irrelevant. The length, L, is 0.3 meters, the speed, 0.25 meters per second, and g, 9.8 meters per second squared. We'll discover that theta max must be equal to 0.1458, roughly, radians. And when you convert that into degrees by multiplying, for example, 180 degrees for every pi radians, you get that this is about 8.4 degrees. Now, in case that all seemed a little bit confusing, often in physics you can double check your calculation by doing it another way. I want you to consider that you can also do this problem by using conservation of energy. Imagine that at the bottom, the object has a maximum speed of v. It swings up to a particular height, at which point it'll have a maximum angle theta max. In doing so, it'll have reached a height of h, and we can use conservation of energy to solve this problem. Think of this as L, this is L. That means that because this distance here is L times cosine of theta max, the height is equal to L minus L cosine of theta max. Conservation of energy, which tells us that the initial energy, 1/2 mv max squared, is equal to the final energy, no kinetic but all potential, mgh, which is mg times L, 1 minus cosine of theta max. If you clean this up, you'll discover that the cosine of theta max must be equal to 1 minus v max squared over 2gl, from which you can find theta max by doing inverse cosine. You'll discover theta max is equal to inverse cosine of 1 minus v max squared over 2gl, and that'll still give you 8.4 degrees.